You have looked at the moon your entire life and never once questioned the most obvious fact about it. The face you see tonight is the same face your great-grandmother saw, the same face the Romans saw, the same face that watched the first humans walk upright on the African plains. In all of recorded history, in all the thousands of years that humanity has lifted its eyes to that silver disk hanging in the darkness, not one person has ever seen the other side, not from Earth, not ever. And you accepted this without wonder. You looked at the moon the way you look at a painting on a wall. It simply is what it is. The man in the moon stares down at you, and you never asked yourself the question that should have kept you awake at night. Why does that face never turn away? Why, in all the moon's endless circling of our world, does it never show us its back? The moon is a sphere, rotating through space, orbiting the Earth once every 27 days. By all rights, we should see every part of its surface eventually. We should watch craters and mountains and vast grey plains rotate into view and then disappear again, just as the continents of Earth rotate past the sun each day. But we do not. The moon keeps one face eternally toward us, as if it were bolted in place, as if some cosmic mechanism locked it into position and threw away the key. I tell you now that this is not coincidence. This is not some miraculous arrangement placed there for our benefit. This is gravity. This is mathematics. This is the inevitable consequence of forces acting over timescales so vast that the human mind recoils from them. And I intend to show you exactly how it works, because once you understand this, you will never look at the moon the same way again. You will see not a static portrait, but a dynamic system, a dance of forces that has been playing out for billions of years and will continue long after the last human draws breath. Let us begin with what you think you know about the moon's motion. You believe the moon orbits the Earth. This is true, but incomplete. You believe the moon takes roughly a month to complete one orbit. Also true, also incomplete. But here is what you may not have considered. The moon also rotates on its own axis. It spins, just as the Earth spins. And here is the fact that should make you pause. The time it takes the moon to rotate once on its axis is exactly the same as the time it takes to orbit the Earth. Precisely 27.3 days. Not approximately, not close enough, exactly the same. Think about what this means. Imagine you are standing on the moon's surface, looking up at the Earth. The Earth hangs in your sky, and it never moves. It does not rise. It does not set. If you are standing on the near side of the moon, the Earth is always above you. If you are standing on the far side, you will never see the Earth at all. Not ever. You could live your entire life on the far side of the moon and never know there was a planet called Earth, because it would always be below your horizon, hidden by the bulk of the moon itself. This perfect synchronization is what we call tidal locking. The rotation period matches the orbital period with absolute precision, and you might be tempted to think this is simply how the moon has always been, that it was created this way, that this arrangement is somehow fundamental to its nature. But you would be wrong. The moon was not born locked. The moon once spun freely, rotating at its own pace, showing all its faces to the Earth in turn. Something changed. Something slowed it down. Something reached across 240,000 miles of empty space and grabbed the moon's rotation and forced it into synchrony with its orbit. That something was gravity. My gravity. The gravity I spent my life describing and quantifying, and I will show you how it works. But first, you must understand tides, not as you learn them in school, not as simple rising and falling of ocean waters, but as what they truly are. Tides are deformation. Tides are the stretching and squeezing of matter by gravitational gradients, and they happen everywhere gravity exists, which is to say, everywhere in the universe. Consider the Earth and the Moon. The Moon pulls on the Earth with gravitational force. You know this. But here is what you may not have fully appreciated. The Moon does not pull on every part of the Earth equally. It cannot. Gravity weakens with distance, and the Earth is 8,000 miles across. The side of the Earth facing the Moon is roughly 4,000 miles closer to the Moon than the centre of the Earth. The side facing away is 4,000 miles farther. This difference matters. The near side of the Earth feels a stronger pull toward the Moon. The far side feels a weaker pull. The centre feels something in between. Now, if the Earth were perfectly rigid, this would not matter much. The whole planet would simply accelerate toward the Moon as a single unit. But the Earth is not perfectly rigid. It is made of rock and water and molten iron, and these materials can flow and deform under stress. The near side, pulled harder, bulges outward toward the Moon. The far side, pulled less hard, effectively lags behind and bulges outward in the opposite direction. The Earth becomes ever so slightly elongated, stretched along the line connecting it to the Moon. This is the tidal bulge. There are two of them, one on the side facing the Moon and one on the side facing away. The oceans, being liquid, respond most dramatically to this effect. They pile up in two great bulges on opposite sides of the planet, and as the Earth rotates beneath them, different coastlines pass through these bulges. When your part of the Earth rotates into a bulge, the ocean rises. When it rotates out, the ocean falls. High tide and low tide, twice a day. A rhythm that has governed life on Earth since the first creatures crawled onto land. But the ocean tides are merely the most visible manifestation of a deeper truth. The solid Earth itself also deforms. The ground beneath your feet rises and falls by about a foot twice a day. You cannot feel it because everything around you rises and falls together, but it happens nonetheless. The rock itself flexes under the Moon's gravitational gradient. Now, turn this around. If the Moon raises tides on the Earth, what does the Earth do to the Moon? The Earth is 81 times more massive than the Moon. Its gravitational influence is correspondingly more powerful. The tidal forces the Earth exerts on the Moon are vastly stronger than those the Moon exerts on the Earth. The Moon is being stretched and squeezed by Earth's gravity far more intensely than we are being stretched and squeezed by the Moon's gravity. The Moon has tidal bulges too, two of them, one facing the Earth, one facing away. And here is where the story becomes truly interesting. When the Moon was young, when it first coalesced from the debris of that ancient collision 4.5 billion years ago, it rotated freely. Let us say it spun once every few hours, much faster than it orbited the Earth. The Earth's gravity raised tidal bulges on the Moon, just as the Moon raises tidal bulges on the Earth today. But because the Moon was rotating faster than it was orbiting, those bulges did not stay pointed at the Earth. The Moon's rotation carried them forward, ahead of the Earth-Moon line. Imagine you are the Moon. You are spinning, and as you spin, the Earth's gravity is constantly trying to pull your tidal bulges toward itself. But you are rotating faster than the Earth can track you, so your bulges are always being carried ahead. They want to point at the Earth, but your rotation keeps sweeping them forward. Now, gravity does not simply pull on the centre of mass. Gravity pulls on every particle of matter, and it pulls harder on particles that are closer. The Earth's gravity is pulling on your tidal bulge, that excess mass that sticks out toward it. And that bulge is not aligned with the Earth-Moon line. It is rotated forward ahead of where it should be. This creates a torque. The Earth is pulling on your forward bulge, and that pull is not along the line connecting your center to the Earth's center. It is offset. It creates a twisting force, a force that acts to slow your rotation. The Earth is reaching across space with its gravity and grabbing your tidal bulge and using it as a brake. This is gravitational torque. This is tidal braking, and it is relentless. Every single rotation of the ancient moon, the Earth's gravity grabbed its tidal bulge and slowed it down by an infinitesimal amount. Not much, perhaps a few fractions of a second per century, but the process never stopped. Over millions of years, over hundreds of millions of years, over billions of years, the moon's rotation slowed and slowed and slowed. Each rotation took a little longer than the last. Each spin was a little more sluggish than the one before. And here is the key insight. The torque depends on the misalignment of the tidal bulge. As long as the moon rotates faster than it orbits, the bulge is carried forward, and the Earth pulls it backward, slowing the rotation. But what happens when the rotation slows to the point where it matches the orbital period? What happens when the moon rotates exactly once per orbit? The tidal bulge stops being carried forward. It points directly at the Earth. There is no more misalignment. The gravitational pull on the bulge is now along the Earth-Moon line. There is no more torque. The braking stops. The system has reached equilibrium. The moon is tidally locked. This is not a delicate balance. This is a stable configuration. If something were to speed up the moon's rotation slightly, the bulge would be carried forward again, and the torque would return, slowing it back down. If something were to slow the rotation below the orbital period, the bulge would lag behind, and the torque would act in the opposite direction, speeding it back up. The system naturally corrects itself. Tidal locking is an attractor state, a gravitational equilibrium that the moon fell into and from which it cannot escape. Let me give you numbers, because numbers make this real. The moon's tidal bulge is not large in absolute terms. The difference in radius between the bulge and the rest of the moon is perhaps a few hundred feet. But the moon is massive. 2.2 times 10 to the 19th tons of rock and dust, and ancient magma. Even a small bulge represents an enormous amount of mass slightly displaced from where it would otherwise be. The gravitational torque acting on that displaced mass, integrated over billions of years, was sufficient to completely halt the moon's independent rotation. The process took somewhere between 10 million and 100 million years. In cosmic terms, this is almost instantaneous. The moon was born spinning freely, and before the Earth had finished cooling from its own formation, the moon was already locked. For more than 4 billion years, the same face has pointed toward us. The current arrangement is not ancient beyond measure. It is simply older than multicellular life, older than breathable air, older than the continents. Now you understand why the same side always faces us. But I have only told you half the story. The moon is locked to the Earth, but the tidal interaction runs both ways. The moon raises tides on the Earth, and those tides are also subject to friction and torque. The Earth is also being affected by this gravitational dance, and the consequences are profound. Remember that the Earth rotates much faster than the moon orbits. The Earth spins once every 24 hours, while the moon takes 27 days to complete one orbit. This means the tidal bulges raised by the moon on the Earth are being carried forward by Earth's rotation, just as the moon's bulges were once carried forward by its rotation. The moon's gravity pulls on Earth's tidal bulges. That pull creates a torque. That torque is slowing the Earth's rotation. Your days are getting longer, not by much, about 1.4 milliseconds per century. You will never notice it in your lifetime, but add it up over geological time and the numbers become staggering. 600 million years ago, when the first complex animals were appearing in the oceans, the day was only 21 hours long. A billion years before that, when life was nothing but single-celled organisms, days were perhaps 18 hours long. When the moon first formed, the Earth may have been spinning so fast that a day lasted only 6 hours. The Earth is slowing down, and it has been slowing down for 4.5 billion years. But energy cannot simply disappear. The rotational energy being drained from the Earth must go somewhere. And it does. It goes into the moon's orbit. When the moon's gravity pulls on Earth's forward-carried tidal bulge, the interaction does not just slow the Earth's rotation, it also transfers momentum to the moon. The moon is being pushed forward in its orbit, accelerated ever so slightly with each tidal cycle. This acceleration does not make the moon orbit faster. Orbital mechanics does not work that way. Instead, the moon moves outward. The moon is receding from the Earth. We have measured this directly. Using lasers bounced off reflectors left on the lunar surface by the Apollo astronauts, we can measure the Earth-Moon distance with millimeter precision. The moon is currently moving away from the Earth at a rate of 3.8 centimeters per year, roughly 1.5 inches. The width of your thumb every year, compounded over the age of the solar system. When the moon first formed, it was perhaps 15,000 miles from Earth, close enough to fill a terrifying portion of the sky. The tides it raised were not gentle swells, but walls of water miles high, scouring the young Earth with unimaginable violence. The moon's retreat has been ongoing ever since, and it will continue into the far future. But here is the question that should now be forming in your mind. If the Earth is slowing down and the moon is speeding up, will they eventually reach equilibrium? Will the Earth become tidally locked to the moon, the way the moon is locked to the Earth? Yes, eventually. Given enough time, the Earth's rotation will slow until it matches the moon's orbital period. When that happens, one side of Earth will always face the moon, and one side will never see it. The day and the month will be the same length. But here is where the mathematics becomes strange. As the Earth slows and the moon recedes, both periods are changing. The day is getting longer, but so is the month, because the moon's orbit is getting larger, and larger orbits take longer to complete. The final equilibrium will occur when both periods match, and the calculations suggest this will happen when the day and the month are both about 47 of our current days long. The Earth will rotate once every 47 days. The moon will orbit once every 47 days. Both bodies will be locked to each other, facing each other eternally, frozen in gravitational embrace. This will take an extraordinarily long time. Current estimates suggest 50 billion years or more. The sun will have long since exhausted its fuel and expanded into a red giant, possibly swallowing both Earth and Moon in its bloated outer layers. The question of mutual tidal locking may be academic, but the physics does not care about the sun. The physics simply describes what would happen if the system were allowed to evolve undisturbed. And what would happen is complete mutual locking. I want you to sit with this for a moment. The moon did not choose to show us the same face. The Earth is not special in demanding this arrangement. This is simply what gravity does to rotating bodies in close proximity over sufficient time. The same forces are at work throughout the solar system, throughout the galaxy, throughout the universe. Wherever a smaller body orbits a larger one closely enough and for long enough, tidal locking will occur. And indeed, we see it everywhere. Phobos and Deimos, the two tiny moons of Mars, are both tidally locked to their planet. Their days exactly match their orbital periods. The same faces always point toward Mars. The four great Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto are all tidally locked to Jupiter. Each one rotates exactly once per orbit, keeping one face permanently toward the giant planet. This is not coincidence. Jupiter is so massive and its moons orbit so close that tidal locking occurred relatively quickly on cosmic timescales. Charon, the largest moon of Pluto, is locked to Pluto, but Pluto is also locked to Charon. They are mutually tidally locked right now in the current epoch, facing each other eternally as they waltz through the outer darkness of the solar system. They have already achieved what the Earth and Moon are slowly working toward. Mercury, the innermost planet, is in a strange partial resonance with the Sun. It rotates 3 times for every 2 orbits, a 3-to-2 spin-orbit resonance that is a kind of cousin to tidal locking, caused by the same forces but stabilized by Mercury's elliptical orbit. Even some exoplanets have been found in tidal lock with their stars. Planets orbiting very close to small, cool red dwarf stars are likely to be tidally locked, with one side in eternal day and one side in eternal night. The temperature difference between these hemispheres would be extreme, hundreds of degrees, creating violent atmospheric circulation and bizarre weather patterns unlike anything in our experience. All of this flows from the same mathematics, the inverse square law of gravitational attraction. The weakening of gravity with distance creating differential forces across extended bodies. The deformation of those bodies into tidal bulges. The torque created when those bulges are misaligned with the gravitational source. The gradual transfer of angular momentum until equilibrium is reached. I spent my life describing these forces with equations. I showed that the same law governing an apple falling from a tree governs the moon in its orbit and the planets in theirs. But even I did not fully anticipate the long-term consequences of gravitational interaction, the slow grinding of worlds against each other's gravity until they surrender their independent spin and face each other in permanent salute. This is what I want you to understand. The cosmos is not static. It appears static because you live for only a few decades and the relevant timescales are millions and billions of years. But the universe is evolving, changing, moving towards states of lower energy and higher stability. Tidal locking is one expression of this tendency. Given enough time, gravity organizes rotating systems into configurations that minimize tidal dissipation. The universe is falling into gravitational equilibrium, one interaction at a time, over timescales that dwarf the entire history of life on Earth. And yet this process is not complete. It is ongoing. It is happening right now. As you read these words, the Earth is slowing by milliseconds per century. The moon is receding by centimeters per year. The dance continues, as it has for billions of years, as it will for billions more. You look at the moon and see a face frozen in place. I look at the moon and see a system in motion, a gravitational engine that has been running since before life began and will continue until the sun dies. The same side faces us not because of luck or design, but because of physics, because of mathematics, because of the remorseless logic of forces acting over time. This is what my gravity does. This is what my equations describe. Not just the arc of a thrown ball or the orbit of a planet, but the long, slow shaping of worlds themselves, the grinding of rotation into synchrony, the evolution of chaos into order over cosmic timescales. And now I will show you the mathematics. The torque exerted on a tidally distorted body depends on several factors: the mass of the perturbing body, in this case the Earth, the radius of the distorted body, the Moon, the distance between them, and a quantity called the tidal quality factor, which describes how much energy is lost to internal friction as the body flexes. The torque is proportional to the mass of the perturber squared. Double the Earth's mass, and the torque quadruples. This is why massive planets lock their moons so quickly. Jupiter, 318 times Earth's mass, exerts torques on its moons that are 100,000 times stronger than Earth exerts on our moon. No wonder the Galilean moons locked so fast. The torque is proportional to the radius of the satellite to the fifth power. This is a steep dependence. Our moon twice as large experiences 32 times the torque. Larger bodies have larger tidal bulges and longer lever arms for the torque to act upon. The torque is inversely proportional to the distance to the sixth power. This is the most dramatic dependence. Move a moon twice as far away, and the torque drops by a factor of 64. Tidal effects fall off extraordinarily quickly with distance. This is why distant moons can retain independent rotation for billions of years, while close moons lock almost immediately. The tidal quality factor describes the stiffness and dissipation characteristics of the satellite's interior. A perfectly elastic body would not experience tidal breaking, because its bulges would respond instantaneously to the changing gravitational field, and no energy would be lost. A perfectly fluid body would dissipate energy extremely quickly. Real bodies fall somewhere in between. The Moon, largely solid rock with a small partially molten core, has a tidal quality factor around 30. This is relatively high, meaning it is relatively stiff and does not dissipate tidal energy quickly. But even so, over billions of years, the dissipation was sufficient. Let me walk you through the calculation for our Moon. The relevant formula for the timescale of tidal locking involves all these factors combined. For the Moon, with its mass, its radius, its distance from Earth, and its estimated primordial rotation rate, the calculation yields a locking timescale between 10 and 100 million years. This is consistent with geological evidence, suggesting the Moon has been locked for essentially its entire history. The same calculation can be applied to any moon in the solar system or any planet around any star. The mathematics is universal. The specific numbers change, but the underlying physics remains identical. For Earth locking to the Moon, the calculation is much longer. Earth is more massive, more distant from its tidal perturber relative to its own radius, and has a different interior structure. The timescale comes out to roughly 50 billion years, far longer than the Sun's remaining lifetime. This is why I said the mutual locking may be academic. The physics permits it, even demands it eventually, but the Sun will intervene first. But the physics remains true. The tendency toward locking is real and ongoing. Every tide that rises and falls on Earth, every flexing of rock beneath your feet, every microscopic friction as water sloshes against coastlines and ocean floors, all of it is draining rotational energy from our planet and feeding it to the Moon's orbit. The process is imperceptible on human timescales and overwhelming on cosmic ones. Now I want you to consider something that seems obvious but conceals unexpected depth. If the same side of the moon always faces Earth, that means there is another side that never faces Earth. A far side, a hidden hemisphere that no human eye ever saw until the space age, that remained completely unknown to every civilization that ever existed before the 20th century. For all of human history, half of the moon was invisible, not because it was dark, not because it was shrouded in clouds, but simply because it was turned away. The far side receives just as much sunlight as the near side. It has its own days and nights, its own phases relative to the sun. An observer standing on the far side would see the sun rise and set every 27 days, just as on the near side. But that observer would never see Earth. The planet that dominates the near side sky, that hangs motionless above the lunar landscape, that rises and sets not at all, that observer would never know it existed unless they walked around to the other hemisphere. When the Soviet probe Luna 3 swung around the moon in 1959 and photographed the far side for the first time, it revealed a landscape startlingly different from the familiar near side. The near side, the face you know, is dominated by vast dark plains called Maria, the Latin word for seas. Ancient astronomers thought these dark patches might be oceans, and the name stuck even after we learned they are actually solidified lava flows, the frozen remnants of volcanic eruptions billions of years old, the sea of tranquility, the sea of storms, the ocean of prodigies. These poetic names mark the smooth, dark expanses that give the man in the moon his features. But the far side has almost no Maria. It is bright and cratered and battered, an ancient surface that records impacts stretching back nearly to the formation of the solar system itself. The far side looks older, more primitive, more violent than the near side. For decades, this asymmetry puzzled scientists. Why should one hemisphere be so different from the other? The answer, it turns out, connects back to tidal locking. When the moon was young, shortly after its formation, it was much hotter than today. The collision that created it, a Mars-sized body slamming into the early Earth, left the moon partially molten. Radioactive elements in its interior continued generating heat, and the Earth, so close in those early days, raised enormous tides in this semi-molten material. The near side, the side facing Earth, experienced stronger tidal heating. The constant flexing as the moon orbited through Earth's gravitational gradient generated friction, and friction generates heat. The near side stayed hotter longer. Its crust remained thinner. When large asteroids struck the moon billions of years ago, the impacts on the near side penetrated through this thin crust into still molten material below. Magma welled up and flooded the impact basins, creating the smooth dark Maria we see today. The far side, facing away from Earth, experienced less tidal heating. It cooled faster. Its crust grew thicker. When the same bombardment of asteroids struck the far side, the impacts could not penetrate through to the magma beneath. The craters remained craters, unfilled by lava, preserving a more ancient and battered surface. Tidal locking did not just determine which face we see. It shaped the very geology of the moon, creating a world with two fundamentally different hemispheres. The gravitational dance between Earth and Moon did not merely lock rotation, it determined volcanic history, crust thickness, surface composition, and appearance. The moon you see in the sky is the moon that tidal forces made. This is what I mean when I say gravity shapes worlds. Not just their orbits, not just their rotations, but their internal structure, their geological evolution, their very faces. The moon is what it is because of where it is. Move it farther from Earth, and it would have cooled more uniformly, locked more slowly, developed differently. Move it closer, and the tidal forces would have been even more extreme, perhaps tearing it apart entirely, or driving such intense volcanic activity that the surface would be unrecognizable. Every world in the cosmos bears the imprint of its gravitational environment. The forces are written in rock and ice and stone. Let me take you now beyond our moon, beyond our Earth, to the moons of Jupiter, where tidal forces operate on a scale and intensity that makes our Earth-Moon system seem gentle by comparison. Io is the innermost of Jupiter's large moons, orbiting the giant planet at a distance of about 260,000 miles. This is close. Jupiter is so massive that its gravitational influence at this distance is overwhelming. Io is tidally locked to Jupiter, as I mentioned before, keeping one face eternally toward the planet. But the tidal forces do not stop at locking. Io is not alone in its orbit. The other Galilean moons, Europa, Ganymede, and Callisto, exert their own gravitational influences. These influences create orbital resonances, patterns, where the moons periodically line up and pull on each other. Io, Europa, and Ganymede are locked in a 4:2:1 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This precise ratio is maintained by gravitational interactions, and it has a dramatic consequence. The resonances force Io's orbit to remain slightly elliptical rather than perfectly circular. In an elliptical orbit, the distance between Io and Jupiter changes continuously. When Io is closer, Jupiter's tidal forces are stronger. When Io is farther, they weaken. This means Io is constantly being stretched and squeezed as it orbits, its tidal bulge growing and shrinking, the rock of its interior flexing back and forth like a ball of dough being kneaded. This flexing generates heat, enormous amounts of heat. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the moon with fresh lava. The entire surface is less than 1 million years old on average, a blink of an eye in geological terms, because volcanic eruptions bury the old surface faster than craters can accumulate. All of this energy comes from tides, not tides of water, but tides of rock. Jupiter's gravity, modulated by the orbital resonance with the other moons, is literally melting Io from the inside. The moon is being cooked by gravity. Europa, the next moon out, experiences similar but less intense tidal heating. Europa is farther from Jupiter and smaller than Io, so the tidal forces are weaker, but they are still sufficient to generate significant internal heat. Beneath Europa's icy surface lies a global ocean of liquid water, kept liquid not by sunlight but by tidal flexing. The ice shell flexes as Europa orbits Jupiter, and the friction warms the interior enough to maintain a liquid layer, perhaps 60 miles deep, containing more water than all the oceans of Earth combined. This ocean makes Europa one of the most compelling targets in the search for extraterrestrial life. Life as we know it requires liquid water, and Europa has an abundance of it, warmed by tides, shielded from radiation by miles of ice above. If life can exist anywhere beyond Earth in our solar system, Europa's hidden ocean is among the most promising places to look. And all of it, the volcanism of Io, the ocean of Europa, the possibility of alien life, all of it traces back to tidal forces, to gravity acting across distance, to the same physics that locked our moon's face toward Earth billions of years ago. Do you see now why I say gravity is the architect of worlds? It does not merely hold things in place, it shapes and sculpts and transforms. It determines which moons have oceans and which are frozen solid. It decides which surfaces are ancient and cratered and which are young and volcanic. It writes its signature in the geology of every body that orbits close enough to feel its influence. Let me turn now to an even more extreme case. Let me speak of planets orbiting other stars and what tidal locking means for the possibility of life in the universe. Most stars in our galaxy are not like the Sun. The Sun is a yellow dwarf, relatively large and hot and bright. But the most common stars are red dwarfs, much smaller and cooler and dimmer than the Sun. Some red dwarfs emit less than 1% of the Sun's light. To receive enough warmth to maintain liquid water on its surface, a planet orbiting such a star would need to orbit very close, perhaps 10 times closer than Mercury orbits the Sun. At such close distances, tidal forces are intense. The same mathematics I described earlier applies. The torque is inversely proportional to the distance to the sixth power. A planet orbiting 10 times closer experiences 1,000,000 times the tidal torque. Such a planet would tidally lock to its star almost immediately on cosmic timescales, within a few million years of its formation. This means that potentially habitable planets around red dwarf stars are likely to be tidally locked. One side would always face the star, experiencing eternal day. The far other side would always face away, experiencing eternal night. The day side would be blasted by constant sunlight, potentially hot enough to boil away oceans. The night side would be frozen, never receiving any direct starlight at all, potentially cold enough to freeze carbon dioxide out of the atmosphere. For a long time, scientists assumed that tidally locked planets could not support life. The temperature extremes seemed too severe. The day side would be a furnace, the night side a deep freeze, and the terminator between them a region of violent storms as hot air rushed toward the cold hemisphere and cold air rushed toward the hot one. But more recent work has revised this picture. Atmospheres and oceans can transport heat from the day side to the night side, moderating the extremes. A planet with a thick atmosphere and abundant water might maintain habitable temperatures in a band around the terminator, the permanent twilight zone where day meets night. Life could exist in this ring of eternal sunset and sunrise, never experiencing true day or true night, looking up at a star that hangs motionless on the horizon. Such a world would be profoundly alien to our experience. The geography would be organized around the sun position. The hottest point would be directly beneath the star, the coldest point directly opposite. Weather patterns would be permanent and stable, driven by the unchanging temperature gradient rather than daily or seasonal cycles. Seasons would not exist. Neither would time zones in any meaningful sense. The entire concept of a day, so fundamental to life on Earth, would be absent. And yet life might flourish there, adapted to conditions we can barely imagine, shaped by the same gravitational forces that shaped our moon and our world. Red dwarf stars are not rare. They constitute roughly 3/4 of all stars in the galaxy. If even a small fraction of them host tidally locked but habitable planets, the universe might be filled with such worlds, far more common than planets like Earth that rotate freely and experience normal days and nights. The cosmos I described, the cosmos governed by my laws of motion and gravitation, is one where tidal locking is the rule rather than the exception. Most moons in close orbits are locked. Most planets in close orbits around small stars are locked. The Earth-Moon system is typical in its physics, if not in its specific configuration. Gravity reaches across space and synchronizes rotation with orbit, creating worlds of eternal faces, eternal days and nights, eternal orientations toward whatever massive body dominates the gravitational environment. This is the universe you live in, a universe where gravity does not merely attract, but organizes, where rotational chaos is slowly ground into synchronous order, where the patient action of tides over billions of years creates configurations that seem designed but are merely inevitable. Let me return now to our own moon and our own Earth, and trace out the future that awaits. I told you that the moon is receding from the Earth at 3.8 centimeters per year. I told you that the Earth's rotation is slowing at 1.4 milliseconds per century. These processes will continue for billions of years, and their consequences accumulate. As the moon moves farther away, it appears smaller in the sky. 4 billion years ago, when it was much closer, the moon would have appeared enormous, perhaps 20 times larger in angular diameter than it does today. The tides it raised were catastrophic. Walls of water, hundreds of feet high, sweeping across the primordial Earth every few hours. As the moon retreated, the tides gentled. Today's tides are modest compared to those ancient cataclysms. In the future, the moon will appear smaller still. Eventually, it will be too small to completely cover the sun during a solar eclipse. Total solar eclipses, those transcendent moments when the moon's disk exactly matches the sun's and the corona blazes forth in sudden glory, will become impossible. The geometry that allows this perfect celestial alignment is temporary, a brief window of a few 100 million years out of the solar system's 5 billion year history. We happen to live in that window. Future generations will not. As the Earth's rotation slows, the days grow longer. Life will have to adapt. Organisms that rely on circadian rhythms, keyed to a 24-hour cycle, will find those cycles drifting out of alignment with the lengthening day. Over millions of years, biology will adjust. Over hundreds of millions of years, the changes become dramatic. A day 50 hours long would be a very different thing to experience than a day 24 hours long. The temperature extremes between noon and midnight would be more severe. Weather patterns would reorganize. The entire rhythm of life would transform. And eventually, if the system were left undisturbed, the Earth would lock to the moon. One hemisphere would see the moon always overhead, the other never. But by then, the sun will have changed so dramatically that the question becomes moot. In roughly 5 billion years, the sun will exhaust the hydrogen in its core and expand into a red giant, its outer layers swelling to perhaps the orbit of Earth or beyond. The moon's recession and the Earth's slowing will be irrelevant compared to being engulfed by the dying sun. But let us imagine, for the sake of understanding, that the sun did not intervene. Let us imagine the Earth-Moon system evolving in isolation for 50 billion years. What would we find? Two bodies, tidally locked to each other, orbiting their common centre of mass once every 47 of our current days. Earth rotating once every 47 days, one face permanently toward the moon, one face permanently away. The moon, locked as it is now, one face permanently toward Earth. From any point on Earth's moon-facing hemisphere, the moon would hang motionless in the sky, never rising, never setting, a permanent fixture at a specific point determined by your longitude and latitude. From the opposite hemisphere, the moon would be forever invisible, always below the horizon. The tides would cease. With both bodies locked to each other, There would be no relative motion to drive tidal bulges around the planet. The oceans would settle into a static configuration, slightly bulged toward and away from the moon, but not sloshing back and forth. The tidal pools that nurtured early life, the estuaries shaped by daily floods and drains, the intricate dance of marine organisms keyed to the tidal rhythm, all of it would end. A static Earth facing a static moon would be a world fundamentally different from the one that gave rise to us. This is the end point. This is the equilibrium toward which gravity is slowly pushing our world. The system is evolving, has been evolving since the moon formed, will continue evolving until something external intervenes. The face you see tonight is a snapshot of a process in motion, one frame from a movie that runs for billions of years. I want to step back now and consider what all of this means. Not scientifically, not mathematically, but philosophically. What does it mean to live in a universe where gravity shapes worlds in this way? It means that nothing is permanent. The configurations we see today are not eternal arrangements, but temporary states in ongoing evolution. The moon's face has been locked for 4 billion years, but 4 billion years is not forever. The Earth's day has been approximately 24 hours for only the most recent sliver of geological time, and it will not remain so. The solar system we observe is not a finished machine, but a process unfolding on timescales so vast that human civilization is less than a blink. It means that simplicity emerges from complexity. The moon once rotated chaotically, at its own pace, showing all faces to all directions. Now it presents one face, always, with mechanical precision. Chaos became order. Randomness became pattern. This emergence of simplicity is not mystical, it is gravitational. Tidal friction dissipates energy, and systems naturally evolve toward states of minimum energy. Those states are often highly ordered. Gravity is an organizing principle, turning the chaos of early rotation into the order of tidal lock. It means that the universe is comprehensible. The same equations that describe the fall of an apple describe the locking of the moon. The same inverse square law that governs a cannonball's arc governs the fate of planets around distant stars. The universe is not arbitrary. It follows rules, and those rules are knowable. A mind armed with mathematics can predict the behavior of worlds it has never seen, can describe the past and future of systems across cosmic time. This is the great gift of mathematical physics. It makes the universe legible, and it means that we are not separate from the cosmos. The same forces that lock the moon are acting on your body right now. The tides that rise and fall in the oceans also act on you, imperceptibly, negligibly, but really, you are embedded in a web of gravitational influence that connects you to the moon and the sun and every mass in the universe. You are not an observer looking at the cosmos from outside. You are part of it, made of star stuff, governed by the same laws, subject to the same forces. This is what I wanted to show you when I began. You looked at the moon and saw a face that never turns away, and you accepted it without wonder. But now you see what that unchanging face represents. It represents gravity operating over billions of years. It represents tidal forces deforming rock and dissipating energy. It represents the slow grinding of worlds into gravitational equilibrium. It represents a universe that is dynamic and evolving and comprehensible and beautiful. The same side of the moon always faces us because physics demands it, because gravity reaches across 250,000 miles and grabs the moon's tidal bulge and will not let it turn away. because energy dissipates and systems seek equilibrium, and order emerges from chaos over sufficient time. Because the universe is not arbitrary, but lawful, and those laws play out on timescales that dwarf human comprehension. You have looked at the moon your entire life. Now you truly see it. You see not a static portrait, but a frozen moment in a dynamic process. You see not a coincidence, but a necessity. You see not a face, but the fingerprint of gravity itself, pressed into the very fabric of another world. And if you look up at the moon tomorrow night, or next month, or next year, you will see the same face, the same craters, the same dark Maria and bright highlands, the same man in the moon staring back at you. But you will understand now that this constancy is not stillness. It is the equilibrium of forces, the balance of torques, the end point of a process that began when the moon was born in fire and violence 4.5 billion years ago. The same side will always face you. Not because the universe is simple, but because the universe is deep. And in its depths, in the patient working out of gravitational mathematics over cosmic time, it creates patterns of such elegance and order that they seem like design. They are not design, they are physics. My physics. The physics of universal gravitation, of inverse square laws, of forces acting at a distance, the physics that connects the apple to the moon, and the moon to the planets, and the planets to the stars. Look up tonight. See the face that has watched over every human who ever lived, and know that you are seeing gravity itself, written in stone twice the age of life on earth, a message from the deep structure of reality, patiently waiting for a mind curious enough to ask why. That is the truth my mathematics reveals. That is the answer to the question you never thought to ask. Now you know.